In this class, we will show you how to use FortiGate High Availability. HA joins two or more FortiGate appliances. Depending on the style you choose, high availability for FortiGate can either increase total throughput or provide an automatic hot standby appliance. We will discuss requirements of both HA styles, how each appliance in the cluster communicates with the others, the differences in load balancing and failover behavior, and how HA behaves during a firmware upgrade. We'll also talk about advanced topics such as an alternate type of HA clusters. When you've completed this class, you should be able to configure, operate, and troubleshoot a FortiGate HA cluster. The idea of HA is simple. HA links and syncs two or more devices. Like HA, you may have seen on other vendors' products one FortiGate act as the main appliance. It synchronizes its configuration to others. It uses a heartbeat link to detect when another appliance becomes unresponsive. How many are linked? What is synchronized between them? Are all FortiGates processing traffic, or is one of them a hot standby? Does HA literally improve availability, or does it improve throughput? Which style is better for me? On FortiGate, the answers vary by the two HA styles, active-active and active-passive. Let's examine the differences. This style of FortiGate HA is called active-passive. As you might guess from the name High Availability, it literally improves availability. Adding an appliance in active-passive style increases reliability with redundant hardware. So it's useful for 99.999% uptime contracts. Downtime may be 2 seconds or less depending on your configuration. Nobody may notice, but it doesn't increase throughput. What makes this active-passive not active-active? The primary is the only FortiGate that actively processes traffic. Standby synchronizes with the primary's configuration, routing, and session tables to remain ready for active duty. But until the primary fails, they are otherwise passive. Traffic does not go through passive FortiGates. This style of HA is called active-active. Like active-passive HA, if the primary fails, a secondary will substitute for the failed appliance. But this style is not as highly available. Active-active is a cluster in the more traditional sense. It increases throughput, and it does this by load balancing. So secondaries are not on standby. Traffic goes through all FortiGates. They each have their own session tables, which are not synchronized. So the session table in the failed appliance's volatile memory is not redundant. If any FortiGate fails, clients must re-establish those sessions with another FortiGate in the cluster in order to rebuild the lost session table. Clients of that failed appliance will notice a traffic interruption. Resuming is fast, but not instantaneous, and failover is not seamless. If FortiGate can provide HA, when is it better to delegate HA to another device? To elect a primary, achieve failover, and/or load balance across the cluster, the FortiGate HA appliance must communicate. This adds some CPU and network overhead. If your FortiGate cluster doesn't utilize much of its system resources, performance differences may be negligible. You may be able to reduce total cost by using FortiGate HA instead of an external load balancer. But if your network is demanding, system resources may be scarce. If your configuration requires intensive processing, synchronization may also be a heavier burden. In this case, you can offload HA to an external load balancer such as FortiADC to improve performance or use VRRP. Connect the load balancer to multiple non-HA independent but identically configured FortiGates. Also configure the load balancer to avoid forwarding traffic to FortiGates that are offline. FortiGate HA requires at least 2 but up to 4 FortiGates with the same firmware, hardware model, VM license, hard drive capacity and partitions, operating mode, transparent or NAT, VDOMs. 1 to 8 links between the FortiGates for the HA heartbeat and synchronization. Redundant heartbeat links are best. If one link fails, HA will use the next by priority positioned in the heartbeat interface list. If all heartbeat links fail and HA communications are totally interrupted, the cluster will stop processing traffic. In a cluster, one FortiGate is the primary. It synchronizes its configuration and sends heartbeat signals to the secondaries. In active-active HA, it also regulates load balancing. More FortiGates in a cluster mean that each must process more HA heartbeat and synchronization traffic. This adds performance overhead, so you'll want to monitor system resources if you have 2 or more secondaries. Balance between fault tolerance and HA overhead. Inadequate heartbeat performance can actually decrease fault tolerance. This is because if the secondaries don't receive heartbeat signals in time, they will assume that the primary has failed and elect a new primary, causing accidental extra failovers. This shows how a cluster elects the primary FortiGate. First step. The cluster compares the number of connected, monitored interfaces. The FortiGate with the most available interfaces becomes primary. If it's equal, evaluation continues. Step 2. The cluster compares uptimes. This is not exact. If the difference is less than about 5 minutes, they are considered to be equal and evaluation continues. Step 3. The cluster compares the device priority setting that you've configured. If equal, note that it is not uncommon to give multiple devices within a cluster the same priority. Then the cluster chooses a primary by the device's serial number. So with the priority override disabled, which is the default setting, the uptime has precedence. To manually trigger a failover, you can use the CLI command diag sys ha reset-uptime. We can alter the order of what clusters consider when electing a primary. If the priority override is enabled, priority precedes uptime. This means you can specify a FortiGate to be the preferred primary. The disadvantage is that each time the primary fails and becomes available again, an extra failover will occur when it resumes the role, taking it from the temporary substitute. This setting does not sync, therefore must be enabled on each individual FortiGate. What else doesn't sync in HA? Host names don't. So you can use them to distinguish between each FortiGate in the cluster when administrators log in. Host names are also in log messages. Otherwise, it would be impossible to know which events had occurred on each device. So what are the roles of each FortiGate in an HA cluster? Whichever primary is currently elected to be the primary, also called a master, controls how the cluster operates. It monitors the cluster by sending hello signals and listening for replies to know if each FortiGate is available. It also synchronizes its configuration to others. In active-active HA, it also distributes traffic among the cluster. The other role is a secondary. This role's behavior also varies a bit by HA style. In active-passive, the secondary simply waits, receiving synchronization data, but not actually processing until the primary stops responding. Then it, or another secondary, if any, attempts to become the new primary. In active-active, though, secondaries don't wait passively. They process all traffic assigned to by the primary. But because their session tables are independent, they are not prepared for rapid failover. This visualizes how the workload is distributed between roles, depending on the HA style. Notice that workload is not distributed in active-passive, but it is in active-active. If a primary fails, it triggers an HA failover. What happens if a secondary FortiGate fails? In an active-passive cluster, the primary only updates its list of secondaries. It monitors for a failed secondary, waiting for it to come online again, but doesn't try to sync to it. In an active-active cluster, though, the secondary was handling traffic. So the primary, which tracks and assigns all sessions, must not only update its list of available secondaries, but it must also reassign sessions from the failed FortiGate to a new secondary. So how do the primary and secondary FortiGates communicate? FortiGate HA uses FGCP, the FortiGate Clustering Protocol, for HA-related communications. FGCP travels between clustered FortiGates over the link that you have designated as the heartbeat. Your heartbeat link should be a cable. If you have another device in between, such as a switch, ensure that it is dedicated and isolated from the rest of your network so that critical FGCP traffic does not need to compete with other traffic for priority or bandwidth, and collisions cannot occur. Notice that FGCP only communicates between FortiGates. How do other devices in your network discover which HA FortiGate should receive traffic? To train your network to forward traffic correctly, FortiGate HA uses virtual MAC addresses. When a primary FortiGate joins an HA cluster, each interface is given a virtual MAC address. Through the HA link, the primary informs all secondaries. Upon failover, a secondary adopts the same virtual MACs for equivalent network interfaces. The new primary broadcasts a gratuitous ARP notifying the network that each VMAC is now reachable through a different port on each switch. So from the network's perspective, it acts as if you quickly disconnected and moved a FortiGate from one link to another. Each switch begins forwarding Ethernet frames for that VMAC through the newly advertised port, the one connected to the new primary. Using a virtual MAC address for the ARP allows your network to adapt to the failover faster. It's not a new MAC address with a new segment, so STP, for example, doesn't need to learn an entirely new spanning tree. They just need to move a known MAC to a different port. This works in most cases, but depending on devices surrounding your FortiGate cluster, you may sometimes also need to use the CLI command set link failed signal enable interface setting. This causes the outgoing primary to bring down all links for 1 second, forcing the network to update. Now we've seen how HA effectively transfers IP addresses from a failed FortiGate to a new one. What about the heartbeat interfaces? You don't need to configure the IP addresses. FGCP will automatically negotiate IPs, assigning them in the 169.254.0 subnet in order of boot up, or if boot was simultaneous, serial number. You can override this if required. Now you know how heartbeat interface IPs are automatically assigned, so you can understand more from the diag system HA status command in the CLI. Here, you see that there are two devices in this cluster. The primary FortiGate's heartbeat interface has an IP of 169.254.0.2. Why is this significant? The IP indicates this FortiGate was not originally the primary, which would have had an IP of 169.254.0.1. A failover has occurred. To discover the cause, you would study the logs and history. Failover has a few possible causes. Let's look at each. When a FortiGate leaves an HA group due to, for example, a broken power supply unit, another FortiGate will automatically take its place. If your cluster is not set up to synchronize sessions, then all communications will be reset. So if someone was in the middle of downloading a file, the transmission would halt. If session synchronization is enabled, the download would momentarily pause while the failover happened and then continue normally. When you notice this kind of failure, you should replace the failed FortiGate as soon as possible. If an interface on the primary is unplugged, the FortiGate can use port monitoring to detect this and remove itself from the HA cluster. With this kind of failover, check for a loose or disconnected cable first. To prepare for failover, HA keeps configurations in sync. Let's study that now. FortiGate HA uses a combination of both incremental and complete sync. When first establishing the cluster, the primary compares all configurations. If any doesn't match, it uploads its complete configuration to that secondary. This propagates your configuration and overwrites all FortiGates in the cluster. After, synchronization is maintained. The primary immediately sends each change. For example, if you create an address object, the primary doesn't resend its complete configuration, just the new address object. HA periodically checks that all are still in sync. If not, it does another complete sync. Again, FGCP keeps all FortiGates in sync automatically. You don't need to manually configure each FortiGate. HA propagates more than just the configuration. Some runtime data, such as DHCP leases and routing tables, are also kept in sync. Normally, event logs record configuration changes as important events. Note, though, that most log thresholds won't record an HA sync, even if it changes all of the configuration. This is because sync is normal for HA. Now that we've seen HA configuration sync, let's show how HA syncs or distributes traffic. Remember, this varies by the HA style. Active-passive syncs most sessions, but active-active basically doesn't. It distributes session load. Here is active-active FortiGate HA handling a TCP connection handshake shown from layer 2 upwards. First, the client side sends a SYN packet. It's forwarded to the primary FortiGate. If the primary offloads the connection to a secondary, then the secondary responds with ACK and starts the back-end connection with the server. Otherwise, the primary does. Next, the client acknowledges the ACK. It's forwarded again to the primary, who signals the secondary. Finally, the server responds to the TCP SYN sent by the secondary. Again, the packet is sent not to the secondary, but the primary, so the primary signals the secondary. As you can see, the primary handles all traffic even when it's not the FortiGate that does inspection. But antivirus inspection, for example, takes more time and processing than simply switching packets, and high-capacity FortiGate models can use link aggregation. As a result, the rate limiter is still often processing, not the speed of the primary FortiGate's interface. Here is more detailed information about session data and which sessions sync to prepare for seamless failover. To support seamless failover, all sessions must be synchronized between cluster members. This way, the standby can quickly pick up sessions where the failed primary stopped. Active-passive clusters provide failover for TCP, UDP, ICMP, multicast, and broadcast traffic. Active-active only provides failover for TCP. With VPNs, IPsec traffic will fail over, but SSL will not. So far, we've discussed FortiGates where each acts as a whole security domain. But if you have an HA cluster with VDOMs, you can configure a virtual cluster. Essentially, each VDOM can use a different FortiGate as its primary device. This acts as a load balancing situation so that the secondary in an active-passive cluster still processes traffic. It also stabilizes the behavior. One thing that is challenging for administrators about the active-active cluster's behavior is that there is no way to predict which device will be used to process inspected traffic. Traffic like ICMP or UDP will only pass through the primary, and an inspected TCP connection may get processed by the primary or secondary. The same as with a standalone device, when upgrading an HA cluster, each updating FortiGate must reboot. However, in a cluster, since there are multiple devices, reboots are done without disrupting traffic. Here's how it happens. First, you upload a new firmware image. If it is an active-active cluster, load balancing is turned off, so all traffic goes through the primary. Primary updates the firmware on all the secondaries, which in turn reboot and rejoin the cluster. Once they rejoin, the primary no longer has the newest firmware, so a new primary is selected, causing a cluster failover. The new primary uploads the new firmware to the old primary, which then upgrades and reboots. The old primary rejoins the cluster. You can configure the old primary to take back its old role, but this is not necessary and causes an extra failover. At the beginning, we showed some simple HA topologies, but we mentioned that they weren't recommended. Now let's look at some more robust HA topologies. If you want to prevent a single point of failure, you can make a full mesh HA cluster. In addition to extra hardware, you also need extra cabling in order for this to function properly. This is more complicated to assemble and administer, but can provide availability required by critical installations. This is only available with higher-end FortiGate models because not all FortiGate models are capable of creating aggregate or redundant interfaces. Therefore, pay close attention when choosing your FortiGate model. Be aware of any hardware limitations if you intend to deploy a full mesh HA. FortiGate Session Life Support Protocol, or FGSP, is an alternative to active-passive HA. It allows per VDOM session synchronization between two FortiGate devices in standalone mode. It requires external devices to load balance sessions between each FortiGate. FGSP was formerly known in previous FortiOS releases as session synchronization. However, the FGSP feature has been expanded to support UDP, ICMP, and NAT session synchronization, as well as configuration synchronization. Sessions are synchronized only if they do not require security profile or UTM inspection. So, FGSP is a simpler solution than HA because traffic redirection is done by external load balancers. In most FGSP implementations, two standalone FortiGates are installed between two load balancers. This is how you configure FGSP on each FortiGate. In this case, the port 2 in VDOM root is used for session synchronization, similar to the heartbeat interface for HA. In the CLI, under Config System Session Sync, specify the IP address of the other FortiGate, the name of the VDOM where the interface port 2 is located, and the name of the VDOM whose sessions are going to be synchronized. As we explained, by default, only TCP sessions with no NAT are synchronized. Usually, due to their non-stateful nature, UDP and ICMP sessions are not required to be synchronized. However, if such synchronization is wanted, you can enable it with the setting Session Pickup and Session Pickup Connectionless. NAT sessions can also be synchronized with the setting Session Pickup NAT. Now it's time for the labs. In this lab, you'll enable, configure, and test HA. You'll also access the management interface that is not used to synchronize the configuration between HA FortiGate appliances clustered into HA.